In this video, we're going to take a look at what are some things that we can do with limits, and we're also going to see a new theorem. So this page right here is somewhere in your book. I don't have the page number off the top of my head, but essentially it's telling us what are we allowed to do with limits. A really common thing that we're going to see in our class is we're going to come up with like a definition, like last time we saw the formal definition of a limit. Other big ones are going to be the derivative, antiderivatives, a whole bunch of definitions. And at first glance, they're really complicated. They're hard to work with as is. So we try to come up with ways to streamline working with those definitions, be it limit, derivative, etc. So here, this gives us a bunch of algebraic tricks that we can apply whenever we're evaluating limits algebraically, since that's the primary way that we're going to find our limits. So what this says is if I have some numbers like L, M, C, K, if those are all real numbers, and if this is a really big, I want to highlight here, think in geometry, if then, cause, effect. If you don't have the cause, you may not get the effect. If you know the limit as x goes to c of f of x is L, and you know that the limit as x goes to c of some function g of x is M, if you know that already, then you can, or a necessary effect of that thing, or what this will cause to happen, are the following things. Basically, you can take limits over a sum or a difference or a product or a quotient and a whole bunch of other things. So essentially what this lets us do is take limits piece by piece whenever we're performing different operations like adding, subtracting, etc., etc. The thing I want to emphasize is you need to know that these two limits exist before you can use any of these algebraic tricks. Also, composition, we'll talk more about that last one there. Essentially, what we're going to do is just plug in and evaluate piece by piece. And this theorem allows us to do that. Why are all of these things true? Well, if you actually take the formal definition of a limit and you do a bunch of algebraic trickery, you can show that you're actually allowed to do all of these things under the assumption that you know the limit of your first function is L and the limit of your other function is M. So that's something that we're going to work with in class. In fact, we kind of already did. We just didn't really call it a theorem or properties of limits or any of that stuff. One thing I want to focus on is this thing called the squeeze theorem. So let's say that you have three functions, h, f, and g. Hypothetical, let's say that you know h is smaller than f, which is smaller than g. In other words, f is sandwiched in between h and g. This is also sometimes called the sandwich theorem. Or I could have said f is squeezed in between h and g. If you know that that's true, and if you know that the limit as x goes to c of h is L, and the limit as x goes to c of g of x is also L, then that means that the limit as x goes to c of f of x has to also be L. They all have that same limit at that point. So here I have a picture, and in fact, I think I drew my picture upside down. The h should be at the bottom and the g should be at the top because h is less than f is less than g. So if you wanted to mentally swap where h and g are, that would make a little more sense. Basically, you have a function up here and then a function down here. You've got the orange and the blue functions. The green function is sandwiched or squeezed in between the orange and the blue functions. As you approach C, it looks like the orange and the green function have the exact same function value, but in particular, they have the same limit. I should have labeled that L over here to the left. So you could also swap this around if G was less than F is less than H, blah, blah, blah. Basically, you have the same limit at that point. So the conclusion of this would be then the limit as x goes to c of f of x would also be L. How is this useful? Well, sometimes we do not know what f of x is, but we know it's squeezed between two other functions, and we know the limit of those two functions is the same. This theorem allows us to conclude the limit of f of x. Another useful thing that the squeeze theorem, or some people call it the sandwich theorem, two useful things actually are these two special trigonometric limits. You need to know them. The first one So I have theta here. You could put an x if you want to. So the limit as theta goes to 0 of sine theta over theta, you might take a guess at this one. It's not what you might think. It actually comes out to be a 1. What? What in the world? And I will prove this with you all in class next time. It uses the squeeze theorem. And then one other one that comes across your way once every so often, almost the same, a little bit different. 1 minus cosine theta over theta. So if you're taking the limit of that thing as theta goes to 0, you actually get a 0. So anytime we see any one of these expressions, sine theta over theta or 1 minus cosine theta over theta, if we're taking the limit as theta goes to 0, these are just two special limits that you really should know. That's basically it for this video, and that should give you plenty of information to get started on those Schoology questions.